Professor Carme Calderer from University of Minnesota, where she is in the School of Mathematics. So it's nice to now have a more mathematical perspective after the experimental research that was presented in the previous talk. Let us welcome our speaker.
Thank you very much to the organizers for the invitation and the Newton Institute, and I want to share my also thoughts about Ukraine, and especially thinking about Valerie. 2 years ago, the father of a friend and colleague in Kharkiv needed very urgent heart surgery, and Oleg helped. And then I contacted Valerie, and he gave us a lot of resources for the logistics. First of all, how to bring him from Kharkiv to Kiev in a safe way, and well, recovery and all this. And especially, we managed to pin down the best cardiologist in the Ukraine, who got permission to leave the war for a couple of days and go and do his surgery. So now the patient is recovered, fully recovered, and you know, just hoping for the end of the war. Thank you very much, and thanks, Valerie, if you are listening. Okay, so I'm going to talk about a theme that kind of approaches related, say, to fracturing soft matter. And the talk has two parts. So, but the common thread is that we study the role of bonding and adhesion of a membrane to its substrate when it's in competition with other mechanical forces. Main goal is to study conditions leading to the bonding in two cases. So the first problem is static. It has to do with the design of protective polymer coatings for body implanted medical devices. So due to the moisture environment, so polymers absorb water and become gels, increase in volume by swelling, which creates stress concentrations, especially near substrates, and possibly leading to the bonding of the coating, the membrane, and the failure of the device. So we did this is static approach following experiments by our team. And the problem came from just a number of years ago. I think I started talking in really over 10 years ago. From there is a medical device company in Minneapolis, Medtronic, and so what happens, for example, they have to do implants. Of course, there's many kinds of implants, but there's ones that are particularly sensitive to the stability of the coatings. And those are these electrodes that are inserted in the brain, say in the case of neurological diseases, for some therapy for these diseases. Then what happens is that these electrodes are very toxic, and they have to be protected from, you know, they have to protect the brain, and they have to, and the same for the heart. So then they put the polymer coating. And one of the issues is that it, you know, it's going to swell and break apart. So then every one of these devices has a number of expected years of life. Sometimes it's 20 years, sometimes it's 5 years for neurological devices. But in any case, it's very much subject to regulations and, you know, expectations. And so they have to try many different kinds of polymers and see how they perform. So to have a mathematical model for them, it helps because they can cut down in many experiments. And also, but the particular reason why this company, you know, contacted us is that they can operate, say, in a fairly safe way if they use commercial software. But as soon as they get into, you know, thin coatings, very often the software just breaks down. So then they needed to take a mathematical look at the problem. And it came out to be quite interesting because, among other things, you see how the wisdom of asymptotics can just break down completely. So that's one of the things that we will address. And the second one is design of shear suppressing membranes for equipment protection in earthquakes. So this comes from Japan. There's a company that work with Yamaguchi and Doi. And so basically what they want to do is, suppose that you have, a very fancy screen, TV computer screen, right, that is on a table. And then an earthquake comes, shaking, there's many in Japan, and of course it falls. So the idea, what we're doing with this is to design a membrane that actually can absorb shear. And so the problem is somehow the counterpart of the problem of pulling a rug. So you've probably seen it at home very often, that if you have a room with with an area rug, not an area rug, a large rug, and you really want to move it, right? It's very hard. It's very hard to pull it. So the trick to move that rug is to make wrinkles, right? So to make bubbles, and then of course you suppress areas of contact, and then you can pull it much easier. Here's the opposite. Okay, so what you're doing here is, suppose that you have, this is your table where you put the TV. Okay, the experiment goes that you have on top of this table, there is going to be a substrate that moves at a certain velocity. And then on top of the substrate, there is the actual film that you want to generate as protected. This film is attached on the left, so it's attached, but of course on top of the substrate. And as you move the substrate, say, to the right, then the film wants to follow, and of course it has to create a lot of shear. And at some point the shear is too much, and it debones. So when it can, say, overcome the forces, the energy of the glue, of the attachment, it's some kind of gluing material. So when it can overcome that energy, and then it's going to detach. As it detaches, of course, then picks up, leaves the shear is zero, but then it picks up bending. So then you get this bend bubble that is not in contact anymore. But this bend bubble now is subject to gravity. And at some point, gravity is going to kind of push it down, gets into contact again, but then another bubble starts. So you get a whole collection of waves that goes this way. Okay, so, right, so this is the first experiments that we got from Metronics, which tell us what's really going on with swelling and detachment. So here, of course, in their devices, there's no device that consists of only one material, right? And for example, in this experiment, you would have two polymers, the upper and the substrate, right? That they have, say, different elastic modulus, different properties. So then you put them in water. So the whole trick here is to put them in water or in some liquid. So then this is really what they would like to happen, because the substrate, say in this case, the upper polymer, say, is very much, it's kind of more rigid, it swells a lot less, but the bottom one picks up a lot of water and makes the top one bend. Then if you, say, run into too much swelling in the bottom, then they kind of break apart, so the glue here, the attachment, really gives up, and then you just have the two separate pieces. That's not what you want to happen. Okay, so, well, you can read some of the features on that. So, and then, so for us, we're looking at a similar situation, except that the substrate, it will be here in the, so, I want to go back. Okay, yep. So the substrate stays in the bottom, and then we have a polymer on top. Right, so now, that's basically the outline. The first part is, as I said, it's static, they talk about gel energy. Then the loss of convexity of that energy, and although today I'm going to deal 99% of the situations in the convex case for the energy, for the elastic energy, so we see that loss of convexity gives rise to cavities and dry spots. So this is basically what is known as the coffee ring problem. So then the mathematical setting is an energy minimization with an obstacle constraint. and then apply the finite element method, look at the challenges due to basically the geometries, then looking at how much energy it is liberated by the bonding, and then talking about 2D versus 3D simulations, looking at validation and computational cost. So there is a lot of this that is actually numerical analysis. And then the second part is the dynamical problem, the membrane attached to the substrate, looking at Onsager principle, and the outcome is the Chalmers waves and the dynamics of the detached and detached regions and conclusions. Okay, so I left the bibliography in with the abstract, so you can go back and look at where everything happens, but this is work that we started actually before 2009, and then later we kind of, well, other people have joined, but at this point, so what I'll talk about today is mostly by, let's see, Duban now, Manuel Sanchez, they are both in Chile, in Santiago, and then Xichen Song and Ronald Siegel, so they are in pharmaceutical sciences, and Xichen Song is also a doctor in pharmacy, but he's also a PhD candidate in mathematics. And he's the one that is doing the experiments. And okay, so, and this is the work with Doi, and it's just the first part, so there's going to be something else hopefully soon. And let's see. So here we are. So how do we model a gel? So gel is thought as an incompressible mixture of polymer and of an elastic solid, say a polymer, and a fluid. So in the reference configuration, the polymer occupies the domain in R3. Okay. The deformation of polymers occurs by gain or loss of fluid. Of course, you can have any other kinds of deformations by forces, but this is what I am going to really emphasize today. So how a polymer deforms by gaining or losing fluid. And this gain or loss of fluid is just not just a sponge effect, but there is some chemistry involved. So the solid, so the polymer, undergoes a static deformation according to the 1-to-1 differentiable map from omega to phi of omega, and that's the Jacobian determinant. And so the domain occupied by the gel after deformation is the image of the original one. So here, you're not going to see many of this, but say the label 1 corresponds to the solid, to the polymer, and the label 2 corresponds to the liquid. So, and this in the case of those membrane coatings that we were talking about, so the water would come, say, from the body and just joins the polymer. Okay, so now a couple of things about, what are the variables that we need. The model is quite simple, so you'll see that it can really be explained in a couple of slides. So if we look at the point Y in the deformed configuration, is like a composite particle, is a homogenized particle that has a volume fraction phi1, of course, between 0 and 1 of polymer, and a volume fraction phi2, also between 0 and 1 of fluid, and we suppose that there is nothing else, so they add up to 1. And mass densities would be written this way, just so for the volume fraction of polymer, and this is the pure density of the polymer, in other words, the mass density that it has when it's by itself, and that gives the density, the mass density of the polymer in the mixture, and the same for the fluid. Okay, and here we are considering what is called an incompressible mixture, where these densities gamma 1 and gamma 2 are constant, but of course, then the density that the material has in the mixture, it can change. So that's why this gives an interesting combination of compressible and incompressible elasticity. And now from the conservation of mass, so if we have a certain amount of polymer, say phi, I should call it phi0, sorry, in the reference configuration, then its volume fraction in the deform is phi of y, and of course they have to be equal because these are constant, so that simplifies, right? And of course, and that gives the pointwise form of the balance of mass, which is the volume fraction of the polymer multiplied by the Jacobian determinant equal to the volume fraction of the polymer in reference. Okay, that's the volume fraction of polymer in the form. By the way, right now I dropped the subindices 1 and 2, and whenever you see phi without, or any variable without subindex, that is the polymer. Okay, and here we start with a reference volume fraction, say, less than 1. So it's nearly impossible. It would take huge amounts of energy to actually create a gel without completely dry. Okay, so there's always going to be some water, some whatever solvent is used. So that's the energy. So then here we take the point of course, that's the elastic energy, right? F is the gradient of the deformation map. And then here there is an energy of Flory-Higgins. So that is a mixing energy that goes to the original works by Flory, that checkerboard pattern of mixtures, right? Different kind of cells occupied by the components. And out of that, we got this energy, which is really, product of the entropic energies of its separate phase. So if this is for the polymer phi, 1 minus phi is going to be for the water or the fluid. And the mixing interaction is just very simple, or very simply looking, which is the product of the volume fractions. So, and this constant chi, this is very, very important, and actually it's important because with its value, you can distinguish the two very different states of the gel. So it happens that if this chi is between 0 and 1/2, you are in a mixing regime. Okay, so when we say a mixing regime, means that the total energy has a single minimum, and that would be the preferred kind of composition, mixture composition of the system. Whereas if chi is greater than 1/2, then this energy, and by the way, here there is this H, so this is the W, the Flory-Higgins, multiplied by the determinant, which is the determinant, of course, that you catch up when you do the, the change of volume form, assuming that it holds, right? But let's assume so. So, and we know that by balance of mass, this phi can be written in terms of the determinant, in terms of J, okay? So then in this case, if this function H, which is this part in the energy, this is still the elastic, with G being the elastic modulus, right? So if this H happens to be non-convex, so that would be this case, then you get two minima, and one is very wet, say, and another one is very dry. And of course, you don't want that, at least for this application. So, and that is completely kind of ruled by this Flory constant, that below 1/2 is convexity and above gives a non-convex regime. And that is relation of the elastic to thermal energy. So that's a model with very, very few parameters, but it can really give a lot of results. And actually, both the physics, so there's two big communities that have worked in gel, so just kind of to simplify it maybe, is the chemical engineering community that kind of started in Japan, and the mechanical engineering community in England and US and so. Okay, so you have to, first of all, bridge cultures to really translate, but okay, with some time that can be done. And, but they all use the quadratic energy. So they all use the Neo-Kochian energy, which we know that mathematically still has some problems. And, but, of course, if we want to compare results, so we could be very happy to kind of look at different situations here, different exponents, but that we kind of leave the experimental field in a way. Okay, so now one very important consequence of the form of the energy is that, well, for a Flory parameter less than 1/2, right, a single phase regime, the energy is polyconvex. And if you look at this homogeneous deformation, so gradient of deformation times some lambda rotation, right? And then this lambda solves the equation. This, remember, that's part of the energy, and gamma is this ratio of the elastic to thermal. So then this has a solution, this lambda star, and this solution is very important in all these studies, because this gives a very special, say, expansion. It's an isotropic expansion. And it turns out that that is the signature of the gels. So that typical isotropic expansion, lambda start. And another thing that is important for this expansion is that if there's no boundary conditions, no constraints of any kind, it is also the deformation with the lowest possible energy. So there is no other deformation, even with, that is non-spherically symmetric, that has lower energy than that. And actually, this mathematically comes from a consequence of quasi-convexity. So this is one of the nice examples where you want to show polyconvexity in class. So since we have an energy that is polyconvex, is W1 infinity quasi-convex, and specifically for this Dirichlet boundary data, Jensen's inequality holds in a way that this right-hand side is exactly satisfied by this, this uniform expansion, this particular lambda bar. Okay, so both integrals in the right-hand side coincide exactly with the energies of this isotropic expansion, and that really, with this, you can show that this state is the very minimum energy. Okay, but what happens if we lose convexity? And let's see, for the sake of timing, let me, so for a moment, and that's going to be the only time where I'm going to assume that chi is greater than a half, in other words, that we lose convexity. So if that happens, then of course, that uniform expansion may not be anymore the state with lowest energy and might get some competitors. So, and then there is roughly two kinds of competitors. One is, if you look at, the case that the material can make a cavity. Okay, and let me move on to the next one. Okay, so what is the other case when we lose convexity? And that's the case when the gel forms dry spots. So in other words, you might get some regions, say, that instead, say, of making a void or making a cavity, the water completely runs out. And they get a piece, you get a site of dry polymer. Here there is a very kind of a very sketchy situation, right? That we want to look at this. So in this case, here you have just a spot of dry polymer. So how does this go about? Okay, so suppose that you look at now spherical reference configuration. So you give the domain and the volume fraction in that reference configuration. And suppose that you have an evaporation event, which is what happens when you leave a cup of coffee right in the evening and you come back next day and you find a whole ring, dry ring of coffee. So then, in principle, here is, if I was to tell you the whole physics of this event, it would be probably 1 hour by itself. But so let us say that this happens because, so I'm going to represent this by the application of a compressive Dirichlet boundary condition, right? In other words, R is lambda times R1. R1 is the radius of this reference configuration, this sphere. And I'm taking lambda to be smaller than the lambda start of the uniform expansion of the natural. So we're compressing. So now here there's two competitors for lowest energy. One is the homogeneous uniform compression, right? And the other one is, okay, let's see. So let's take another look here. So this would be this. So it has compressed with respect to, say, it has a radius less than R1. And in this case, okay, so leave the gel at the deformation lambda star, right, the one that likes, but then make a hole here and you remove all the water, you remove it from the center. So that's what effectively happens. So then that corresponds to, of course, to the two solutions that we're talking about here. One is this uniform compression, and the other one is take a wall in the middle, center 0 radius R delta, at the center of the reference configuration, and leaving polymer exposed in that center wall, and everyone else leave it in the happy state. Okay, so this is not difficult to calculate, right? So, and so you look at the volume fractions, R sub lambda is the radius of the dry spot, that we find because of continuity requirements, right, between the two deformations in the spot and outside. But you see here, the solution has the volume fraction of polymer 1, so meaning there is no liquid at all, it's a dry region. And then the other one is equilibrium, the preferred. Okay, so now let's see. So you look at this, so there is a little bit of a stability analysis that goes on with this, but let me show you this. So if we have kappa, let's see, here we have E2. E2 is the energy with the dry spot. And, okay, I can read my own writing here. Oh, sorry, I did it. I had relabeled it different, but that's okay. So, let's see. This is the energy of the configuration with the dry spot. And this is the uniform compression. And that is for chi 0.65. Then go a little bit higher with chi. And you see that, let's see, the uniform compression starts going up. And finally, say you go chi 150, and you get the uniform compression that is much more energetic than the dry spot configuration. There is an energy barrier that you have to take into account around 5, but that's basically, what's going on. So the phase separation in that Flory energy so favors single solutions from this point of view. So now you could do the same with, let's see, and time goes fast, so since the idea is quite the same, and I'm not going to go to the void case, but the void case would compare the opposite, say a uniform expansion bigger than the preferred one, and then this configuration where instead of removing the water, now you completely remove the polymer. So you get a void. Okay, so now this is for many of the problems, actually, yes, that's the main problem I'm going to talk about for the first part. So this is the reference configuration, and I just want to emphasize this. So we have a film, say the length is L, the width is W, and then we have a thickness D, okay? So, and now what we're looking at is, so we start with only part of the film, this kind of pinkish here, that is bonded, okay? It's bonded in the reference configuration, and outside this pink area, it's not bonded. So there is no attachment, there is no glue, okay? So, and here we assume a bonded fraction delta, anywhere between 0 and 1, and we can go to exactly 0 and exactly 1 with some care, but delta times L would be the length of the bonded area in reference configuration. So that is, let's see, yeah, so this gamma is exactly this square here, the pink square, the bonded square. So that's a typical dimension, 90 millimeters to 15 in width. Maybe we experiment with several. And thickness, we kind of focus on 162 and 3 millimeters, right? And well, the first idea of doing asymptotics, after all, the ratio of D over L is quite small. So that can lead you to a lot of trouble. And we'll see why. And then together with the three-dimensional problem, we are also looking at the two-dimensional problem for several reasons. And the two-dimensional problem, basically everything is uniform in this direction of W. Okay, so now let's see. So this is the setup of the energy. We're going to use U, the displacement, maybe rather than Y itself, or although F is again the gradient of deformation. Now the admissible set. So we look for H1 solutions, right? So in other words, the function and the derivative are square integrable. Then, because of the balance of mass, the determinant is not actually greater than 1. It's greater than 1 if you start with a dry polymer, but it's going to be, okay, greater than 0.8, whatever the initial volume fraction is, 1 to 1. And then what we want is this displacement to be 0, right, in this area that I call the bonded area, the pink area, which is x1 less than delta L over 2. So then we define, let's see, the energy. Let's see, here there will be some other constraint that will come. Okay, so then we want to minimize this energy. The elastic plus, actually it's just written here. And also here we put gravity, okay? Sometimes it's relevant, sometimes it's not. So we want to minimize in this invisible set U delta, but subject to this obstacle condition. So basically this is the form, say vertical, well, it's the vertical deformation, right? The direction perpendicular to the substrate, and this has to be greater or equal than 0. So basically you have to have that film always on top of the table. And that's something that in the lab, you don't see it because in the lab it's always on top of the table. But then when you do the calculations, you see that you get configurations below. So that's a kind of Signorini problem. Okay, and then of course, gravity will help to bring things down. So gravity would help actually to the thing to go, the film go below the table if you would impose the Signorini condition. And for the two-dimensional problem, we have U and V to be the displacement map. Okay, so here, unfortunately, I can't say very little about this because, okay, so for K less than a half, so H is convex, so the total energy that has the Newhockian plus the part that comes from the determinant, right? It comes from the mixing energy. This is polyconvex, and in 3 dimensions, the existence of minimizers still remains an open problem for the F-squared growth. However, in 2 dimensions, we do have this theorem. So there exists a minimizer that, in addition, satisfies the obstacle constraint. And the proof is really adapts the proof of Stefan Muller in 1990, high integrability of determinants and weak convergence in L1. So, unfortunately, this I cannot really add anymore because that's how things are. Okay, so let's see. Next, right. So now we want to take care of the obstacle condition. In other words, that this thing. Yeah. So I know I'm always going 12, right? Yes. We do a relaxation. In other words, we're adding this term with A very big, and this penalizes very severely any deformation that goes below the substrate. So then, by an argument of gamma convergence, we can see that the minimizers, and that's 2D, because 3D we can't say anything, so the minimizers actually satisfy or approach the obstacle problem as this A goes to infinity. Okay, and I'll skip the proof because only one part that took more work is to find the lower bound of the energy, but the rest is gamma convergence pretty much. Oh, okay. Oh, I saw that was the time, so no, that's fine. Okay, right. So, yeah, we got the details in the papers, but basically probably this proof cannot improve a lot of the more fancy results that we're going to get from many members of the audience in talks. So I will just go over it. Now, what is interesting is the numerics. So we use this penalization approach for the constraint, right? And then we use third-order finite element discretization in 2D and quadratic in 3D. And these are really things that are perhaps the most, our main contributions, say, in the numerics of this problem. Because in the parts where the membrane is free, of course, you would like to use, say, 0 stresses there, right? But it turns out that, we were getting very large errors. So then we replace that free, say, surfaces with kind of maybe more restrictive. So one is the free slip condition. And also, by numerical experiments, we realized that even in the detached part, the kind of the bottom of the film does not really separate itself very much from the substrate. So we just use 0 tangential conditions. Okay, and then for the Newton's method, we use this incremental softening technique, which means that you're taking initial guesses, starting with, say, with elastic modulus, maybe 1,000 or even 10,000 times greater than the megapascal region that values that we have for the material. Okay, and so this is what we see in the lab, right? So after the gel has been synthesized, so then you do swelling, and that's what we get from the numerics. And actually a comparison of numbers and values of the formations, different spots, give a really very good agreement. And also here we have the deformed configurations for very different deltas. So the green part corresponds to the part where the gel is attached, right? And the gray part, the part where it pretty much swells freely. Okay, and this is for different bonded fractions and different film lengths. Okay, I will show, well, I'll have to go back to this for an observation later, but so now the question here is to answer. So what films are safe, say, that are not going to make things fall apart, okay? So then we borrowed the Griffith criteria for solid fracture, right? So if the free energy release by detachment of the gel is insufficient to compensate the energy required for detachment, then the breaking of bonds will not be observed. So the critical case is when the energy release rate by detachment, which is the derivative of the rate of change in energy per unit of increase in the bonded area, okay? So that's exactly the same definition that comes from solid fracture. And here it just happens to be the derivative with respect to delta, the attached part, of the minimum energy. So when this is greater or equal than sigma is the, let's see if I put it somewhere, sigma is, it's called the adhesive toughness. And it's the energy that is required, I think here, to the bond a unit area. So it's the energy that you need to break the glue, say. So the critical then, in terms of D, we want to do it in terms of the thickness, right? So for fixed delta, okay, that's less or equal than sigma. So this is the minimum energy among the deformations such that are attached in this part with bonded fraction delta, and they are debonded outside this inner region delta. Okay, and it turns out that from this, you can calculate the critical thickness of the film, that if you go below that thickness, you can predict that the film will detach. And here's it. So here, what we have is a calculation of the minimum energy. I think that's, okay. Calculation of the minimum energy with respect to the bonded fraction. Okay, and here, let's see. One is the 2D. This is for the 2D model, and this is for, oh, no, so we have 2D and 3D. Okay, so let's see. Okay, so here there is an observation that it takes more energy to the bond, the 2D film, so theoretical means 2D, than the blue is the 3D film, so it's going to take more energy. So what it means in terms of these calculations, excuse me. So what it means is that the thickness, the critical thickness predicted by the 2D model is greater than the critical thickness of the actual 3D model. So then this can be used because if you want to play it safely, so you cut down the thickness at the 2D prediction. Okay, so if you want to refine, then of course you go to the 3D prediction. Now, what happens is that there is a huge difference in computational work when you do the 3D versus the 2D, but very big difference in CPUs. So, and well, that's, let's see here. Okay, so now really we have to push that. Okay, so before that, so the rest is perhaps more of a numerical analysis discussion of how to use the 2D predictions to simplify the CPUs of the 3D. But I'll skip that. So that was very interesting for of course, for the manufacturer, and it's still safe. Okay, the other problem. Okay, so this is this moving substrate, blue one, that it kind of moves to the right with a velocity u. And the green part is our film, okay? And then at the beginning, you see you start pulling, and there is some shear that builds up here. And then, well, at some point, it's going to start to detach from the end. And then this detached region, this bubble, kind of keeps moving left and more keep appearing. So the question is how many and how fast are they going to travel? So that's what we wanted. Okay, so again, the basic mechanisms here is build-up of shear. Too much shear breaks the substrate bonding, okay? And then as soon as, if this region now goes to the interior, that it does, okay? So then you get this bubble, and this bubble now has no shear energy, but has bending energy plus gravitational. Okay, so but eventually, gravity might bring it down, and you have this kind of appearing and disappearing of bubbles. So that's kind of the story. And let's see. So this is just a simple kind of cartoon of the deformation. So what's important is the top surface of this film is slightly different than the rest. It's inextensible. So you can think of this as an extensible line. And what I'm going to present now is more a rod than a membrane. So it's just the cross section. Okay, and so this line deforms to this. Tau, of course, the tangent vector, and n is the normal vector. And now you see the cross section kind of deforms into this cross section. So there is a horizontal deformation, which is the shear. So after everything is said and done, by the way, maybe the only thing that to remember here is that, let's see, where is that? The top line deforms into, has two deformation components, so U and V, and the top line itself, at capital H, which is the height of this, is X of S, the horizontal, and H of S is the vertical, and that's really what we care about. So it gives the form shape of this top line. Okay, we work out the energy, and then we get an elastic energy, and of course this is going to be elastic energy, which is quadratic in the second derivatives, and then we get a gravitational energy, and this is also part of the elastic energy. Okay, so now if we look at some time after things happening, so this is already the outcome, so we're going to end up with a number of attached regions, attached intervals in this case, x0, x1, x2, x3, and of course every other one is an interval where the film is detached, and that's this. And okay, so then what we don't know is the number of unknowns, in other words, the number of segments that we have attached and detached, and we don't know their location. So that's part of solving the problem. So the unknowns of this problem are the shear, the formation of the top of the film, this H, and then this capital N, kind of N segments, attached and detached, and the total number of these segments. So we have to solve the problem for this, and now this has two parts. So first of all, suppose that we look at a specific time, right? So then we have a problem which is minimizing this energy. Okay, so suppose everything is frozen and you just want to look for the shape of the bubbles. So then here we have a bending energy, a gravitational energy, and of course this is for the detached segments, right? This also kind of goes with that. And then we have the shear energy for the attached segments. So altogether is a sum of energies of detached segments, there's say T sub I of them, and that's the energy of the attached segments. So now the first part of the problem is determine the shape of one of the detached segments, one of these 2i minus 1 2i, And so we have to minimize this energy, but only this part, not the shear one. And now subject to this boundary condition. So you see that there's 4 boundary conditions for H as the fourth of the problem, and there's 2 boundary conditions for gamma because the problem is has only first derivative in gamma. Okay, so these are basically natural boundary conditions, except for the last one, where we use some kind of asymptotic argument to actually see that we can set it to 0, and that was making the numerics a lot easier. Okay, so then when you have minimized this, right, so you get, say, gamma, H gamma tilde and H tilde, which are the minimizers, but these minimizers depend on parameters which are actually the locations of these intervals. And that would be, say, at this time t. So at the end of the day, so the minimizers are just function of the locations of those points. And so now the second part of the problem is also variational because we use Onsager's principle to determine the dynamics of the exabytes of these points. So we set up the rate of dissipation, which is x dot square, sum of x dot square, the rate of dissipation function. And then this is the relation, which is the time derivative of the energy plus the rate of energy dissipation. And now minimizing this, and with this I finished, we get the solution to the problem. So this is the profile of a bubble at some time, and this is the profile of shearing that in a bubble, so the shearing basically goes to 0 after it has decreased from this value gamma of an attached interval. So then the algorithm combines, starts with time discretization at time tn, and then, oops, sorry, that's, oh no, I did that. So that's really the final stuff here. So, and here we get, say, it's a log plot. So this is the velocity of the wave, so the motion of these bubbles, versus the velocity of the substrate, the wall, it says here. So that is what we get, the blue line, and this one is what they get in the experiments. So we had a fairly closed loop. And this is a kind of histogram with the number of attached points. So this n sub delta is the number of attached regions. Actually, these are detached. Okay, and that is plot against the substrate velocity against the length of the film. And so now, with this I just finished. Okay, so this problem still needs a lot of work because it turns out that if the speed of this substrate is, say, below a certain threshold, you get a transition, completely different dynamics. So then the dynamics becomes chaotic. Okay, so right now we've got very nice waves, and now this is chaos. And, okay, that's other stuff in the membrane problem that we're doing about an interpretation of the debonding in terms of critical stresses. And also we are looking into a situation where we consider the degradation of the adhesive with time. That might be important. Now we also we're taking a look at the shape separating regime because that seems to be a good, possibly good model, say, to study the formation of protein aggregates, say, that come in some neurological diseases. So thank you very much.
Thank you for this wonderful mathematical but practically very relevant presentation. Questions? Yes?
So this number of segments, is it fixed or it seems to depend on...
Let me go back. Hold on. You're referring to this?
Yeah, this number of segments. Yeah, right. So that's in experiments now?
That's the result of the model.
It's a model.
Yeah, but it's very close to the experiment.
So it's an unknown of the problem.
What?
The number of segments.
That's the number of, let's see, this would be the number of bubbles.
Yeah. an unknown of the problem, or
it is an unknown of the problem. Yeah, you solve, in addition to solving for the mechanics, right, and shear and bending and so, gravity, you also solve for the location of the bubbles and the attached regions. But the picture, yeah, oh, no, go ahead.
No, I had a different question. So if you go to 23, slide.
Which one?
23, slide 23.
Oh, okay.
Yeah, there. I mean, in defining this D max, you also have D there, right? So
these are the thickness of the film.
right. But in D max, you
Oh, okay, yes, yeah. You just picked that right. Okay, this is the other part of the story, and that's what because, you see, if you look at, so this is the energy, right? But the energy release rate is the derivative of the energy with respect to delta. So what we found is that it's constant. Okay, and this is a way to write it. So that is, oops, sorry, what am I going down? I think the next one, or the previous one. Yeah, so if we kind of look ahead from this slide, this is a constant. And actually, there is quite a lot of story going with this. So why would you find that, at least to the first order, the energy release rate is constant? So in other words, you have lines, it's constant slope, right? So, and this can be explained, so at least intuitively, analytically, it's further. I don't know if there's any job here, right? Thank you. So that can be, and this is where some of the asymptotic issues are coming in. So suppose you have this membrane, right? So this is just attached, nothing happens, right? And now you swell it. So, and suppose that is, say, attached from here to here, so that's not going anywhere, right? So then you see that in a very general way, there are two regions, right? One that has some obstacle, so some constraint in terms of swelling, and this one is quite free. So once you kind of go away a little bit from these ends, this could pretty much behave like free swelling. And in fact, that's what happens. So what happens is, let's see, let me do that. So when you do that, okay, I'm just going to be a little bit maybe brutal in this picture, right? So you see this part, if it swells, the only thing that it can do is pretty much swelling up, right? Because on the sides, it's kind of, okay, so then say to here, okay, well, that comes, it's not completely flat, but, and however, these other parts, they kind of, they are free. And maybe they do something like this. Okay, that is something that has ears like that. Okay, so then what happens? So if, okay, one thing that you could actually, solve the problem by boundary layers, right? So boundary layer between, this is uniaxial extension, and this is, say, isotropic expansion. But let me put here a little question mark, because this is kind of important. So that is and that's what we believe for quite a long time, right? But then what happens is that this is a lot more complicated. But when you have, so if this delta, if this portion of attached, say, it's bigger than 1/2, okay, then if you look at the formation of the cross sections, it's pretty much uniform all the way around. Okay, so look at it this way. When you calculate the energy, which is what you use then for deriving the energy release rate, so it turns out that the energy, this one, say, does not contribute very much, because that's in the happy kind of, free swelling. So what contributes here is what the main contribution comes from this region. And if in this region say, now for other more complicated issues, it's pretty much uniform on these cross sections, that kind of brings this particular pattern on the energy release rate. So this has two advantages in a way, that once you have realized this, then the three-dimensional calculation of the energy release rate really gets simplified by a lot. It really kills the CPUs, that. And just because of this observation, because really you only have to worry about this. You don't have to do the whole problem. And okay, so I can probably tell you a little bit more details of, because this is if you look at some leading, say, analysis or some leading approximation. If you look at some approximation with respect to V, say some asymptotics, and you see that the energy is linear in D at the leading. Okay, that comes a little more complicated, but that's it.
So we're already about 12 minutes behind the schedule.
Yes,
so
of course, it's lunch, and that's not...
Yes, maybe let's thank our speaker one more time for the wonderful